So let's work through some examples of drawing Lewis structures. So our first example here is ammonia, or NH3. So let's go through the different steps of drawing a Lewis structure. So the first step is to determine the total number of valence electrons of all of the elements in the formula. So typically what I do is just take inventory of all of the elements, count up their valence electrons. So we have nitrogen, and then we have hydrogen, but there's three of them. All right, so now let's look at the periodic table and just determine each of these elements what their number of valence electrons are. So number of valence electrons. So for nitrogen, there are 5 valence electrons, and then for hydrogen, there's 1. But because there's 3 hydrogens, we're going to multiply that number by 3. And so our total number of valence electrons for this entire molecule is 8 valence electrons. All right, so that's step 1. Step 2 is to adjust for charge on the molecule or ion. So let's take a look at the charge. If there was a charge on this molecule, it would be to the upper right of the molecule, but in this case, there's an understood 0, that this molecule is neutral. There is no charge. So because this is neutral, we don't have to change the valence electrons at all. So we're going to maintain our 8 valence electrons. All right, so step 2 done. So step 3 is now to determine the skeletal structure. And part of the skeletal structure is we need to identify the central atom. So the central atom usually is the first atom in the formula. So in this case, nitrogen is our central atom. So the only time when the central atom is not the first element in the formula is when hydrogen is like the first element listed, because hydrogen, since hydrogen can only make one bond, it's never going to be the central atom. That wouldn't make sense because you can't put multiple things around a hydrogen atom. Usually hydrogen will be dangling off, it'll be the outer atom or element in a molecule. So, okay, so we've identified the central atom. So I'll draw a nitrogen here, nitrogen, and then you just put bonds, single bonds to all of the remaining elements. So there's 3 hydrogens, so I will draw 3 hydrogens with a single bond on all of them. All right? And so remember, each of these bonds contain 2 electrons. So that takes us to our fourth step, distribute electrons to the non-central atoms according to the octet rule and electronegativity. So what we've have drawn now, our skeleton structure, if we count up the number of electrons, there's 6 electrons here. But we want to get to 8 electrons. So we need to figure out where are we going to put those 2 remaining electrons. So in the fourth step, it says distribute electrons to non-central atoms according to octet rule. So are we going to put the electrons on the hydrogens? No, because these hydrogens already have their octets filled. Because remember, each of these bonds have 2 electrons. So hydrogens, each of these hydrogens have a fulfilled octet, because hydrogen is one of the exceptions where its octet, it only wants 2 electrons. So each of these hydrogens are good. All right, so we don't have to put any extra electrons on hydrogen because they already have a complete shell. So then the fifth step is place remaining electrons on the central atom. So since we didn't put any electrons on hydrogen, we're going to put them on the central atom, which is nitrogen. So as drawn right now, I'll erase these boxes. Drawn right now, there are 6 electrons in those bonds. So those last 2 remaining electrons will go on the nitrogen. So now if you count up the total number of electrons in bonds and lone pairs, this molecule as drawn has 8 valence electrons, or 8 electrons. So this is the overall Lewis structure of ammonia. Oh, sorry, I didn't. So once you place the remaining electrons on the central atom, now you need to check, is the central atom electron deficient? So let's count how many electrons are around nitrogen. So we're asking ourselves, does nitrogen obey the octet rule? So if we count, there's 1, 2, 3, 4, 5, 6, 7, 8. Yes. So nitrogen, if I draw our box, nitrogen has 8 electrons around it, so it is happy, its octet is fulfilled. So if we were drawing the actual Lewis structure without all of, my extra nonsense, it would look like this. All right. Okay, so that is ammonia, a simple case where there's only single bonds. So let's look at an example now where in the fifth step, the central atom is, no, it is not electron deficient. So it's not this example, it's the next one. So let's just do this example, sulfite. So, um, so we're going to do the same step. So let's, step one, determine total number of valence electrons. So that means let's take inventory. So we have a sulfur and we have 3 oxygens. Sulfur has 6 valence electrons. Oxygen also has 6, but there's 3 of them. So that equals 18. So total number of valence electrons is 24. All right, so that's step one. Step two, adjust for charge. So the charge here is -2. So this negative charge means we have to um, need to add 2 electrons to the valence electrons that we have. So because we have a -2 charge, we're going to add 2 electrons. So we have a total number of 26 valence electrons. So remember, if the molecule, sorry, if the ion has a negative charge, you have to add electrons to your valence electron count. So the sign of the charge does not match whether you're adding or removing electrons. So if it's a negatively charged ion, you add electrons. If it's a positively charged ion or cation, then you have to remove electrons. All right, so 26 is our magic number that we need to draw when drawing out this Lewis structure. So again, so step 3, determine skeletal structure, which means we have to figure out what is our central atom. So here, remember, central atom is usually the first atom in the formula. So in this case, sulfur is our central atom. All right, so we're going to start with sulfur in the middle, and then we're just going to put some oxygens to make our skeleton structure, all with single bonds. So I have drawn 6 electrons so far because there are 2 electrons in every bond. So that's step 3. Step 4, distribute electrons to non-central atoms according to octet rule and electronegativity. We don't have to worry about electronegativity because there's only oxygens around sulfur. So let's start on the outside of the oxygens and put electrons on our oxygens. So I have 6 so far, and we want to obey the octet rule. So each of these oxygens are going to get 3 pairs of electrons. So we have 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So if I've drawn 24 electrons so far, I just like to write it down so I can keep track. So now, as drawn, all of these oxygens have full 8 octets. They have 8 valence electrons. So we have 24 electrons drawn. We need 26, so let's take our last step, place remaining electrons on the central atom. So since we have 2 electrons left over to hand out, we'll just stick them on our sulfur. So oxygen has its octet fulfilled. Let's look at sulfur. Sulfur has 1, 2, 3, 4, 5, 6, 7, 8. So sulfur is also happy with a full octet. So everything has a full octet. And then typically what we do if it's an ion is we draw a bracket around the whole thing, and we write that it has a -2 charge, or 2 minus charge around the whole thing. All right, so everyone's octets are happy, and we have 26 valence electrons drawn in our Lewis structure. All right, so let's move on to our next example, formaldehyde. So now I will show you an example where the central atom isn't as straightforward. So this formaldehyde, or also in organic chemistry, when you learn naming convention, it's also called methanal, not methanol, it's methanal. So again, let's take inventory. So we have hydrogens, 2 of them, a carbon, and an oxygen. So hydrogen has 1 valence electron, but there's 2 of them. Carbon has 4, oxygen has 6. So total, there are 12 valence electrons here. It doesn't have a charge, it's neutral. So it's neutral, so we don't have to add anything. So our Lewis structure needs 12 valence electrons. Step 1. Step 2, what is it? Adjust for, we did that. We did step 1 and step 2. Number of valence electrons and adjust for charge. Step 3 is draw the skeleton structure. So what is the central atom? So here's an example where the central atom isn't the first element listed. So the first element listed is hydrogen. I told you hydrogen can't be the central atom because hydrogen can't have more than one bond to it. So it doesn't make sense to put it in the middle. So in this case, let's do a different color. Carbon will be our central atom because hydrogen can't be a central atom. All right, so let's just stick a carbon. I don't like red. Carbon there, all right? And then we need to place 2 hydrogens. All right, and then oxygen. So now I have drawn 6 electrons so far, but I want to get to 12. So I just like to keep that in mind. When we get to our next step is to place remaining, distribute electrons of the outer electrons, or sorry, of the outer elements. So we want to follow electronegativity here. So oxygen is much more electronegative than hydrogen. So we're going to place electrons on oxygen first. Also, hydrogen, these hydrogens already have their octets fulfilled. So we don't have to add anything else to hydrogen. They're already happy. So we're going to place the remaining electrons on oxygen to fill its octet. So we have 6 electrons left. So 1, 2, 3, 4, 5, 6. So now oxygen's octet is fulfilled. And then the last step is to place remaining electrons on central atom, but we already placed 12 electrons, so we're not going to place any more electrons. But then with this last step, you have to check that the central atom is not electron deficient. So let's count how many electrons are around carbon. So carbon only has 6 electrons around it, but it needs 8 to fulfill its octet. So if you are electron deficient and the central atom does not have enough electrons in it to fulfill its octet, what you want to do is start making double bonds to fulfill its octet. So remember, oxygen and carbon were some of the examples elements that can have double bonds. So those exceptions where you tend to see multiple bonding occur or double bonds occur in carbon, nitrogen, and oxygen. So we have oxygen and carbon right here. So this is where an example where we need to place a double bond. So I'm just going to move these pair of electrons to I'm going to swing them down to make a double bond. So I have not changed the number of electrons at all. I am just relocating this lone pair on this oxygen to produce a double bond. So I'll just redraw this whole structure. So we have the oxygen, but then there's a double bond, and I didn't do anything to hydrogen. All right, I forgot my lone pairs. All right, so since I moved one lone pair to make a double bond, that leaves 2 lone pairs left on that oxygen. So this will be our completed Lewis structure. So you can go ahead and count all of the valence electrons around each of the elements. You'll see that oxygen, as drawn, has 2 double bonds and 2 lone pairs. So that's a total of 8 valence electrons around oxygen, so its octet is filled, and carbon has 4 bonds around it, so there's also 8 valence electrons. So carbon has its fulfilled octet, and then both of these hydrogens have a single bond, so there are 2 electrons, so also hydrogen has its filled octet of 2. Right? Okay, so there's that example. So then our last example here for Lewis structure is carbon monoxide. So CO, carbon monoxide. See how there's only 2 atoms here? You don't have to worry about central atoms when there's just 2 atoms because it doesn't matter if you put the carbon here and the oxygen here or the oxygen here and the carbon here. It doesn't matter. You don't have to identify a central atom because there's no central atom when it's only 2. So again, same steps. Let's take inventory of valence electrons. So we have a carbon and oxygen. Carbon has 4, oxygen has 6, so we need to place 10 valence electrons. Carbon monoxide is neutral. There's understood 0, so neutral, so we're going to place 10 valence electrons. All right, so that's step 1 and 2. Now draw the skeleton structure. So carbon, oxygen. Again, doesn't matter if you put oxygen then carbon, it's the same thing, right? We don't have to worry about a central atom. So that's our skeleton structure. Next is distribute electrons on outer elements first. Since there's not necessarily outer elements or outer atoms because there's no central atom, we need to place electrons in terms of electronegativity. So remember what electronegativity is, tendency to have electrons. All right, so we're going to place the electrons on the more electronegative atom first. So if you look back at your electronegativity chart from chapter 6, you'll see that oxygen is more electronegative than carbon, so we will place electrons on oxygen first. We already have 2 electrons in our bond, but we need to get to 10. So let's start at 2, 3, 4, 5, 6, 7, 8. So I've placed 8 electrons total. Oxygen now has a full octet. So our last 2 electrons, 9, 10, will go in carbon. Because remember, we place electrons on the more electronegative atom first. All right, so that's step 4. Last is place remaining electrons on central atom. Well, we already placed all our electrons, but then that last step is you need to check the octets of everything. So oxygen here has a filled octet. There's 8, but carbon does not. So carbon only has 1, 2, 3, 4. Only has 4 electrons. It only has 4 electrons, this carbon. So we need to get 4 more carbons, and the only place we can get them are on these lone pairs on oxygen. So what I'm going to do here is I'm going to move this lone pair on this oxygen to form a double bond. That will give carbon 6 total electrons, but we still need 2 more. So then what I'm going to do is take another lone pair to make another bond to form a triple bond. So now carbon, I can redraw this now. Carbon will have a total of 8 electrons. So since I moved 2 of oxygen's lone pairs to form a bond, that only leaves us with 1 lone pair on oxygen. So that stays there. So again, when we're with that last step in step 5, when you're filling deficient octets, you're just rearranging electrons on atoms. You're just turning lone pairs on atoms and making them into double or triple bonds. We're not adding any more electrons because we've already placed our 10 electrons. We're just rearranging them. So if we check, so this is our Lewis structure, but we can also check our octets. So remember, triple bond has a total of 6 electrons on it. So if we take a look at carbon, carbon has 8 because you get 6 from that triple bond. And then oxygen also has 8 because of the 6 from the triple bond and the 2 from the lone pair. Oop. All right, so that is carbon monoxide. So let's dive a little bit deeper into Lewis structures. This brings us onto resonance, which is a feature that we see when drawing different Lewis structures. So essentially what resonance is that for some molecules and ions, there's actually more than one valid Lewis structure that you can draw. With all of the atoms in the same positions. Essentially, you can just move some of the lone pairs into double bonds or move some of the double bonds into lone pairs. All these different figures or Lewis structures that you draw still obey the octet rule and obey the rules that we spelled out. So the question is, which structure is correct? But in actuality, they're all correct. So what chemists actually observe. So here's an example of a substance that has more than one Lewis structure. So ozone. So ozone is O3. So in total there are 18 valence electrons. So if you count up the number of bonds and lone pairs on this molecule that you see drawn right here, you'll count 18 valence electrons. So you see in this figure, or in this Lewis structure, you see that there's a double bond on one side of the molecule and then a single bond on the other side of the molecule. So remember a few slides back where we talked about bond order. So as you go from a single bond to a double bond to a triple bond, those bonds lengths get shorter and the bonds overall become stronger. So you would predict, looking at the structure, that this end of the oxygen of ozone will have a shorter bond than the single bond side, that this side will be longer than this side. But actually, when chemists, put ozone and look at it under, like electron microscopy, and actually look at the bond length, or crystal structures or something, they actually see that this oxygen-oxygen distance and this oxygen-oxygen distance are the same. So we're seeing essentially, we're saying that this side and the left side and the right side of the ozone molecule is equivalent. So the question is, why is that? Because when we draw out the Lewis structure, we see that we have a double bond on one side and a single bond on the other side. So it doesn't, Lewis structures in this scenario doesn't completely match what we see experimentally. So this is where resonance structures come into play. So with this next slide, so we're diving a little bit more deeply into ozone. So we could probably do this experiment. If I asked everybody in the class to draw ozone, to draw the Lewis structure of ozone, and I told you that it was O3 and that there were 18 valence electrons in ozone. Some people might draw the double bond on this side, on the left side of the molecule. Maybe other folks will draw the double bond on the right side of the molecule. So both of these structures are correct. That if you count up the valence, the octets of all of the oxygens, they all are 8 and good. So I'm telling you that both of these structures are correct. So when ozone exists in our atmosphere, is that ozone is actually represented by the combination of these two structures. Both of these structures exist at the same time. That doesn't mean that the structure of ozone flips back and forth between these two. It doesn't necessarily flip between. We're not seeing like the double bond being over here or it's over here. We're not like flipping back and forth. What it actually is when we see ozone exist in our world, is the average. We see an average of these two structures. So one side of the molecule isn't necessarily, we can't define it as a bond order of 2 and then the other one has a bond order of 1. It's not necessarily the case. We actually see an average of the two bond orders. And that's why when chemists look at the bond lengths between these oxygens, the values are the exact same, because we essentially have an average between 1 and 2, a bond order of 1 and 2. So you could kind of think as the bond order between these oxygens are actually 1.5, which is completely possible. So it's not necessarily a truly single bond. It's not necessarily a truly double bond. It's somewhere in the middle. All right. And so, yeah, so it doesn't flip back and forth. It's the average of the two resonance structure, and that's why the bond lengths are equal on each side. So, if we kind of summarize this, we have like a bond order of 1.5. So that double bond is kind of smeared across the entire molecule. I didn't put lone pairs in because that gets confusing. I just want you to look at the bonds, that double bond isn't locally located on one side of the molecule. So let's define resonance. So resonance is just a way of describing delocalized electrons. So what we're saying is that double bond, the electrons in that double bond are delocalized across the entire molecule, because sometimes it's on the left side, sometimes it's on the right side, and then sometimes it goes back. So it just, it doesn't flip back and forth, but it just kind of exists on both sides at the same time. And it gets smeared across the entire molecule. So how did I want to define this? A way of describing delocalized electrons within a certain molecule Not all molecules have resonance structure. This is just one example. In one molecule where bonding cannot be described by a single Lewis structure. All right, so let's look at another example of something that undergoes resonance. So here's nitrate ion. So let's draw out that Lewis structure. So I saved some time here. Nitrate has 12 valence electrons. Remember that there's this -1 charge, so we have to add that extra electron to get 24. So I'm going to draw out the Lewis structure. I'm going to put nitrogen in the center because it's listed first. I put these oxygens around. So I need to get to 24 electrons. So I have 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. All right, so now I stop. Um, so that's all of the electrons. I placed all of them on the outer atoms. I don't have to put any on the central because I've run out of electrons. There's 24. Now I can look at the octets of everything. All those oxygens have 8 electrons. It's good. But this nitrogen here only has 6 electrons. So we need to form one double bond. All right. But now the question is, so nitrogen's octet is short 2 electrons because there's 6. So we need to form a double bond. So the question is, which oxygen do we choose to form a double bond? Do we pick this oxygen? Do we pick this oxygen and form a double bond here? Or do we put the lone pair on this oxygen here? Or do we pick this oxygen? So there's a bunch of different options that we can choose. So if I ask this question to the whole class, maybe the person next to you will choose a different oxygen. So this is an example of resonance. So we know that we do have to move one of these lone pairs somewhere to the nitrogen. One of them will be. So these are the 3 possible forms that you could have made. We could have chosen the left oxygen to form the double bond. We could have picked the bottom one, or we could have picked the right one. All of these are correct. So if as long as you had the right number of lone pairs around the oxygens and 2 single bonds and a double bond, your answer is correct. So all of these different structures follow the rules that we set out. So any one of those oxygens could have donated that double bond to fulfill nitrogen's octet. So do we see this? When we look at a nitrate ion, let's say in X-ray crystallography or something, if we measured the nitrogen-oxygen bond, would one of them be shorter and one of them be and 2 of them be slightly longer? No, it's not. So what we actually see experimentally, all nitrogen-oxygen bond lengths are equal. All right, so that's why I say here, experimentally, all bonds look alike. It's somewhere between a single bond and a double bond. So essentially, what's happening is that maybe I'll circle like this. These 2 electrons in this double bond delocalize itself across the entire molecule. So instead of a purely bond order of 1 or 2, we actually see there are 4 pairs of electrons being shared over 3 different positions. So the bond order is actually 4/3, or a little bit more than 1. It's like 1 1/3, right? So the nitrate ion that you see is a combination of the average of all 3 of these resonance structures, where that 4th pair, that double bond is delocalized and spread out over all 3 positions. But it's difficult to convey resonance in when you're drawing. If I asked you to draw a nitrate ion, I wouldn't expect you to draw all 3 of these. Typically, 1 is fine. But you just have to know that there are additional resonance structures, and you should be able to identify how many structures are equivalent to one another. All right. And so here is another example of a substance that undergoes resonance. So benzene used to be the world's universal solvent, but then they realized that it is a reproductive toxin, particularly to men. So benzene has a structure that looks like this, where there are 6 carbons in a ring, and then there are 3 sets of double bonds where they alternate. So you can kind of see, if you remember that a double bond is just 4 electrons. So what you could do is take 2 of those 4 electrons in a double bond and move, and that double bond could essentially just swap over to between another 2 carbons. So if I move electrons from this double bond to this single bond, I can move this double bond here and this double bond here. So everyone just kind of moves over 1 seat. So that would be like if there were 6 chairs in a circle and 3 people, and they were all like alternating, and then everyone just moved 1 seat over. That's essentially what's happening here. So now you have a double bond in these 3 locations. So these 2 structures do look different. They are different. All right, but they both follow Lewis structure rules. Every carbon's octet is fulfilled, so both of these structures are correct. So Benzene, sometimes we depict it, instead of actually writing out the carbons and hydrogens, we use this line structure. All right, so this structure is equivalent to the line structure on the bottom here, and this structure is equivalent to the structure down here. And so you can kind of see that these double bond lines, now you can clearly see it, that they're just switching over to the next seat over, essentially. So you can kind of see, you can see really clearly now that these electrons can be constantly moving, that they're delocalized, that sometimes this electron pair is over here, sometimes it's over here, or maybe it could move over here or over here, and it's just going to move around. So benzene is oftentimes depicted as, instead of having purely alternating like single bond, double bond, single bond, double bond, it's actually an average of all those bonds. There's three double bonds, there's three single bonds, so you can take the average and just say, okay, all those bonds have the average bond of like bond order of 1.5. So oftentimes people will just draw a circle around the whole thing, because all of these bonds are equivalent. That if you actually measured this, that all of the bond lengths would be the same. So here I have predict the relative carbon-carbon bond lengths in these two depictions. So in the left depiction, so we know that bonds, so double bonds, are shorter than single bonds. So single bond is longer. So if the left depiction was correct, was the actual structure, we would see a long bond, then a short bond, then a long bond, then a short bond, and it would alternate. But actually what we actually see is all carbon-carbon bonds are the same length. And that's what we actually see. And that's because the bond order, the carbon-carbon bond is equal to 1.5, essentially. So it's the average between 1 and 2.